So actually, the work that I will present today is a part of the PhD thesis of Théotime ASSELIN. But he started a new job in Framatome last month, so he couldn't make it. So I will try to replace him. So the thesis was co-supervised by myself and Olivier from Framatome, and with the contribution of some other colleagues from our laboratory, Institut Péprim in France. So this is a brief outline of my talk. I will say a few words about the context of the study. Then I will present you the different experimental techniques that were used during this study. And then I will move to the results with the determination of the opening and closure strains as a function of loading conditions, for instance. And I will finish by showing how these data can be implemented in a fatigue crack growth analysis, and I will conclude my talk. So as regards the context of the study, so it is, of course, related with the fatigue design of components used in nuclear power plants. And in this context, the fatigue analysis will concern both new projects of power plants, but also the life extension of existing nuclear power plants. And all this raised the need for more accurate analysis, in particular as regards fatigue crack growth, and try to take into account the effect of crack closure. So the components which are concerned with this type of analysis are shown here, mostly pipings and components of a steam generator. And in these components, you have different thermal loadings that may induce low cycle fatigue loading, typically due to shutdowns, restarts, and so on. And the point is that at the moment, we have quite a large number of data on fatigue crack growth rates and crack closure for austenitic stainless steels, such as 304L, but mostly as regards crack closure for load positive stress ratios and small-scale yielding conditions, and typically much less data concerning a low alloy steel used, for instance, in a steam generator. So the improvements that are required at the moment is to get more information about crack closure for characteristic loading conditions, including large-scale yielding conditions, and also try to define a crack drying force parameter that can take into account the effect of crack closure. So in this study, we considered two characteristic materials, as I said, the 304 stainless steel used in pipings and the low alloy steel used in steam generator outer shells. The idea is also to have a ductile material here with a low yield strength, and the material with a higher strength here to show if we have significant differences in closure behavior. As regards the experimental approach that was developed throughout this study, first we performed some reference tests at positive stress ratios using standard fracture mechanics compact tension specimens in order to establish the reference DADN versus delta K curves. And you have some examples here for the two materials. Oh, sorry. And then we performed uniaxial tests again at positive stress ratios using cylindrical notch specimens in order to check that we were able to reproduce the same type of data on this type of geometry. And finally, we perform low cycle fatigue test with negative strain ratios, typically -1, using specimens with a rectangular section area. And we introduce an EDM defect as a crack starter. And this will be the main focus of my presentation. So here you have an example of the experimental setup. So the sample is placed here. Here you have the camera used for digital image correlation analysis, the strain gauge for the strain control, and you can see also the wires which are placed on both sides of the initial defect in order to monitor the crack length during fatigue loading, but also, as we will see later on, to perform some crack closure measurements. So in order to perform the crack closure measurements, we used this type of loading. So here we have the standard fatigue loading, and from time to time, we reduce the load frequency and perform the series of steps during a loading cycle for both the image acquisition, but also for potential measurements. So as regards the determination of the opening or closure strains, we used, as I said, digital image correlation analysis. But the main point here is that we used a method that has been developed in our institute by Valérie Val, which is called the heaviside Dick technique, which is a non-continuous Dick technique. And the main interest is that by using this technique, we can handle discontinuities within the studied area. So these discontinuities can be a slip band, a grain boundary, twin boundary, and so on, but also a crack. This will be the case in our study. The other point is that by using this technique, the crack opening is a direct result of the analysis, but the counterpart is that the computations are much longer, typically 10 times as compared to standard digital image correlation analysis. So here you have a comparison of mapping obtained using the two techniques, the standard Dick and the H-Dick technique. And for instance, here you have a comparison of the displacement along this direction using the two techniques. And you can see that when using the standard Dick, the accurate position of the crack tip is not very easy to determine, while using the H-Dick technique, you have a clear definition of the crack tip location. So we use this technique to determine the opening and closure strains. But actually, we did not necessarily use the crack opening values, as I said, which are directly obtained by the analysis, but we mostly use a digital extensometer that we can place at different distances from the crack tip. And in that case, I will present data obtained at 100 micrometers from the crack tip. So here is a typical result obtained in a case of low alloy steel with a strain amplitude, total strain amplitude of 0.2, a strain ratio of -1. So here you have the loading part of the cycle, and in green, the unloading part. And you can see that in this part, you have a variation of the crack opening as a function of the applied strain. And here we have a kind of plateau corresponding to the part of the cycle where the crack is closed. And by this means, we can determine the value of the strain for crack closure or crack opening. You can see that in that case, we have a small difference between these two values, but the important point is that in both cases, the corresponding strain is a negative strain. And we also used the DCPD technique, which is basically used for crack length monitoring, but by using the different, sorry, I cannot go back. Using the different steps, we can record the value of the potential drop as a function of the applied strain again, and we can clearly identify two regimes. This one, where we have a slight variation of the potential as a function of the strain, can be attributed to crack tip blunting or things like that. And this abrupt transition and large variation of the potential as a function of the strain corresponding with the part of the loading cycle where the crack is closed. So in this graph, we have plotted the U ratio, which is defined as the ratio between the strain range where the crack is fully open divided by the full range, determined by the HDIC technique for the two materials, and in the case of the low alloy steel for two different values of the strain amplitude. You can see that regardless of the material and the strain amplitude, we have the same type of behavior, an initial increase of the value of U, and then a kind of stabilization for the larger values of the crack depth here. And this was consistent also with the measurements performed using the DCPD measurements. Here you have the mean curves obtained by the HDIC technique, and here the points corresponding with the closure strain determined by the potential measurements. And so we have quite a good agreement between these two techniques. And again, since in that case, especially the stabilized value is higher than 0.5, that means that crack opening and closing take place for a negative value of the strain, of the applied strain. Then we tried to see how we can use this data in order to reconcile the fatigue crack growth rate data obtained under different loading conditions. So for that, we introduced the delta kg parameter defined like this from the previous determination of the G integral. But instead of considering the full range, we used the effective strain range experimentally determined in order to introduce a delta effective value of delta kj. So the J value was determined by a finite element analysis. And just to finish, here are the results, for instance, for the low alloy steel, where we compare the data obtained on the compact tension specimens, small scale yielding, and some large scale yielding conditions with a strain amplitude at 0.6. And you can see that using this delta kj, effective value of delta kj, we can reconcile the different set of data. We have the same type of results for the 304L material with a larger scatter. So, but we have less data on this material. So this is a brief summary of my presentation. Thank you for your attention, and I'm ready to take your questions.